Let's talk about the graph of a rational function. So to do that, I'm going to draw a graph of f of x is equal to x squared minus x minus 2 over x squared minus 7x plus 12. It's a rational function because I have variables in the numerator and denominator in a way that the numerator is a polynomial and the denominator is also a polynomial. So I think at some point in this, it's going to be helpful to have this in factored form. So the first thing I'm going to do is factor it. So the numerator factors into x minus 2 times x plus 1. And the denominator, let's see, that's an x minus 4 and an x minus 3. Okay, so let's first talk about how about the intercepts. I want to know, where does it cross the x-axis? Where does it cross the y-axis? So let's talk about the x-intercepts first. So x-intercepts. That is where you are on the y-axis. So y is equal to 0. So I'm going to set my whole function equal to 0. I have essentially a fraction is equal to 0. So a fraction is equal to 0 when the numerator is equal to 0. Or you can think about, I'm going to cross multiply, so x minus 4 times x minus 3 is 0. So that goes away. So I end up with 0 is equal to x minus 2 times x plus 1. That has solutions x is equal to 2 and negative 1. So my x-intercepts are going to be at 2, 0 and negative 1, 0. All right, how about my y-intercept? Well, y-intercept is when you are on the y-axis. That means x is equal to 0. So f evaluated at 0 is going to be a 0 minus 2, that's a negative 2, times a 0 plus 1, that's 1, divided by a 0 minus 4, that's a negative 4, times a 0 minus 3, that's a negative 3. So a negative 2 over positive 12 gives me a negative 1/6. So my y-intercept is 0, negative 1/6. Okay? Another thing I'm going to care about is the domain of this function. And I don't have any square roots, so I don't have to watch out for that, but I do have a potential for dividing by 0. So if you take your denominator, which again, factored form was x minus 4 times x minus 3, and I want to set that equal to 0 because anywhere that x minus 4 times x minus 3 is equal to 0 means I have a 0 in the denominator that can't be in my domain. So that's going to happen when x is equal to 4 and x is equal to 3. So the domain of this function is negative infinity up to but not including 3, union 3 to 4, and then union 4 off to infinity. Okay? There are no common factors to cancel in this function. You can see that they don't share any factors in common, so I don't have that possibility of a canceling out of my 0 in the denominator is also 0 in the numerator. So both of these domain issues are going to give rise to a vertical asymptote as well. So let me rewrite this function down a little bit lower so that we can see it, and then we'll work with our vertical asymptote. So just write it down. We have vertical asymptotes at x equals 3 and 4 because the denominator is 0, but the numerator is not. So I want to figure out what's the behavior of these vertical asymptotes. So let's get my function down here. F of x is equal to x minus 2 times x plus 1 over x minus 4 times x minus 3. Okay, so let's figure out the behavior, what's happening there. So let's say we're approaching 3 from the left-hand side. Now I already know right around 3, this function has explosive behavior, really big up or really big down because x equals 3 is a vertical asymptote. What I want to know is as I'm coming in from the left, is it going up or is it going down? So all I care about is the sign of the function as I approach 3 from the left. So a number that is really close to the 3, but just to the left of it is like a 2.9. So if I plug in 2.9 into my function, I get a 2.9 minus 2, that's positive. 2.9 plus 1, that's positive. 2.9 minus 4, that's negative. And 2.9 minus 3, just negative, but it's still negative. So overall, this is positive. So as x approaches 3 from the left, y is approaching positive infinity. As x approaches 3 from the right, something like 3.1 would be a number just to the right of 3. 3.1 minus 2 is positive. 3.1 plus 1 is positive. 3.1 minus 4 is negative. And 3.1 minus 3 is just positive. So overall, that function is negative So my y is approaching negative infinity. So if we start drawing a little bit of this graph, I have vertical asymptotes. Let's say x is equal to 3 is right here, which is the one I'm working on. And I know I'm going to get to x equals 4 here in a second. So put a little space in there. My graph, as it approaches 3 from the left-hand side, we said that y is going to positive infinity, so it should be up here. And as x approaches 3 from the right-hand side, we said y was going down to negative infinity, so it should be down here. Okay? Let's figure out what's happening with 4. So as x approaches 4 from the left-hand side, a number just to the left of 4 is like 3.9. If I plug that into the function, 3.9 minus 2 is positive. 3.9 plus 1, positive. 3.9 minus 4, just negative. 3.9 minus 3, positive. So overall, it's negative, which means y is approaching negative infinity. As x approaches 4 from the right, a number just to the right of 4 is like 4.1. So 4.1 minus 2, positive. 4.1 plus 1, positive. 4.1 minus 4, positive. 4.1 minus 3, positive. So overall, positive, which means y is approaching positive infinity. So if I add those thoughts into my graph, as we're approaching 4 from the left, we should be down here because we're going to negative infinity. And as we approach 4 from the right, we should be up here because the y's are going off to positive infinity. Okay, since I have my graph started, let's see what else did I have. We had that 0, negative 1/6 was the y-intercept. So let me add that to the graph. So 0, negative 1/6 is going to be like right there. And then I had 2 zeros, or 2 x-intercepts, and those were at 2, 0, and negative 1, 0. So 2, 0 is right about there. So there's 2, 0. And negative 1, 0, let's say, is right about there. Okay. The other thing I want to know is what's happening out far left and far right. So that's the end behavior. And my original function, it's way up there, but just so I don't have to scroll up again, it was x squared minus x minus 2 divided by x squared minus 7x plus 12. So I'm looking for horizontal asymptotes. And I can see that the degree of the numerator is 2. The degree of the denominator is 2. So it's going to level out at essentially to x squared over x squared, or a ratio of the leading coefficients, which is a 1 over 1, which is 1. So my function should behave like y is equal to 1 far out left and far out right. So let's say here is y equals 1. Let's say over here, y equals 1. So when I get over there, I should look like those lines. So if I combine these thoughts together, let's see what my graph looks like. And I already know all the places that it can hit the x-axis and the y-axis. Those are already on there. So the only places I can touch the x-axis and the y-axis is at one of those 3 dots that I already have on. So if I'm up here and I'm supposed to behave like that over there, to the right, well, it probably looks something like this. If I have to be down here and then I have to get over there, it means I have to turn around somewhere. And I know that I can't hit the x-axis, so it's not going to turn around up here, so it's going to turn around down there somewhere. I have to be right here for the vertical asymptote. Oh, I got to hit this point. I got to go through there, and I got to hit this, and then I got to start behaving like that as I get out left. So it probably, give or take, looks a little something like that, which is a really good improvement from, I have no idea what that graph looks like when we started this too. It looks roughly like this. The highs or the lows, like this right here, might be a little higher, might be a little lower, but I do know it is below the x-axis, otherwise I would have had another 0. So that's the idea behind graphing rational functions.